Now that we've talked about impedance for a purely resistive component in a circuit and a purely inductive component in the circuit, let's think about what happens if we were to connect a resistor and an inductor in a circuit, first in series and then in parallel, where there's an alternating source. And let's see if we can analyze that circuit using this new idea of impedance. So the first thing is we need to understand something called an impedance diagram. And so an impedance diagram allows us to represent the different impedance values in the circuit and how we might add them together. So if I had strictly a resistor in the circuit, I know that the impedance is purely a real part in terms of the way that we write it, and this has an angle of 0. So if you have a purely resistive component in a circuit, it means that the current through the resistor is in phase with the voltage across the resistor, and that's why this angle is 0. And we could represent that in an impedance diagram in terms of our complex numbers as being along the real axis. And I'll come back to this a little bit later. If I have an inductor in the circuit, then I can determine what the inductive reactance is for that inductor and that particular oscillating source. And remember, the reactance is telling us how much that inductor is resisting the flow of electricity. And it has an angle of 90 degrees, and that 90 degrees tells us that if you have a purely inductive component in the circuit, that the voltage leads the current by 90 degrees. And of course I can write that in our complex form as having a purely imaginary piece. So that would lie on the vertical axis. So if I wanted to add these two impedance values together, I now have a way of doing that using this complex notation where I can combine a resistive piece in the circuit with a reactance piece in the circuit, and I can add them in the complex plane and say that there is some overall impedance, and that all overall impedance is just a combination of these two values, and there is some angle that tells us how much of this impedance is resistive and how much of this impedance is reactance. So using our notation, we can find the magnitude of the impedance by taking using Pythagorean's theorem, and we know one side is resistance and the other side is reactance, so it's the square root of the resistive piece squared plus the reactive piece squared. And I can find the angle by using the inverse tangent of the opposite side, which is the reactance piece, and then the adjacent side, which is the resistive piece. And I know there's a plus minus here. If it's strictly inductive, then the inductive piece is always going to have a positive imaginary part, and so that angle will always be positive. That's not going to be the case when we talk about capacitors, so that's what that plus minus is there for. And of course, if I knew what the impedance value was, and I knew the angle, I could figure out how much of that impedance was resistive. So what is the piece that's on the horizontal or the real axis by taking the impedance value times cosine of the angle, and I could figure out how much of the impedance was reactive, like an inductor, by taking the impedance times sine of the angle. So everything we learned about complex numbers and writing things in terms of polar form and rectangular form is going to tell us a lot about the impedance. So by using the rectangular form, we can figure out the resistive piece and the reactive piece, and then knowing those pieces, we can figure out the total impedance, which is going to allow us to figure out how the current in that circuit relates to the voltage that's applied across the circuit. So the nice thing about AC circuits is that basically everything that we learned about DC circuits is still valid for AC circuits, with the caveat that we have to make sure that we analyze AC circuits using phasor notation. So Kirchhoff's voltage law is still satisfied. So if I had a number of impedance components where these impedance values could be combinations of resistors and inductors, resistors and capacitors, capacitors and inductors, whatever they may be. There's some overall impedance, and those impedance values are connected in series, and then there is some voltage that is applied across these that is sinusoidal varying. I know that the voltage that's applied across those impedance values has to equal the voltages across all the components. In other words, the voltage rise, which is the source, has to equal all of the voltage drops. According to the equivalent of Ohm's law for AC, I know the voltage across the first component is just the current times the impedance of that component, and the voltage across the second component is the current times its impedance, and so on, where all of these currents through components that are connected in series are exactly the same. So there's no source connected here, but you have to imagine that there's some AC source connected here. There's only one loop possible, and so the current through all of those components is going to have to be the same. Since the current is the same, I can factor that out, and then I end up with all of those impedance values added together. I can say that that is equivalent to some total overall impedance in the circuit, and I have something that looks like the equivalent of Ohm's law, V equals I instead of R, it's impedance, where this total impedance in series is just the addition of the impedance values. So essentially, when you have components in AC that are connected in series, the overall impedance is going to add together. The current will be the same through all the components, and the voltages have to add up to the source, just like if we had resistors for DC. So let's see if we can apply this to an example. So I have a resistor, 4 kilo ohm resistor, and a 2 Henry inductor, and they are connected in series, and across those two components I have a voltage that is varying sinusoidally in time. It has an amplitude of 10 volts, it has an angular frequency of 1000, and it has a phase shift of positive 30 degrees. We want to determine the overall impedance, the current that's flowing through both of those components, and the voltage across each component. And we want to sketch those and figure out what is the phase difference between the voltage source, this one here, and the current. And maybe also what is the phase difference between the voltage across the resistor and the inductor. So we start off by realizing that the total equivalent impedance in this circuit is just the impedance of the resistor plus the impedance of the inductor. So I need to be able to write down the impedance of each one of these components. The impedance across the resistor is just 4 kilo ohms with an angle of 0, and I could write that just as a real part of 4 kilo ohms. And the impedance across the inductor is going to be the reactance of the inductor, and it's going to have a phase angle of 90 degrees, as it always will if it's a purely inductive piece. So we need to figure out what is the inductive reactance for that component. And we realize that the inductive reactance is the angular frequency times the inductance. The AC source has an angular frequency here of 1000, and the inductance is 2 Henry. So if I take 2 and multiply by 1000, I get 2000. Using radians and Henry, I get ohms. 2000 ohms is equivalent to 2 kilo ohms. Since my resistor is in kilo ohms, I'm going to use kilo ohms here. And so I can write down my impedance for the inductor as 2 kilo ohms with an angle of 90, or in terms of rectangular form as 2 kilo ohms in the imaginary direction, or having an imaginary part. That means that the total impedance in the circuit is 4 kilo ohms resistance and 2 kilo ohms reactance, and that's the imaginary part. And I know that in terms of imaginary numbers, I can convert that into polar form and write that as 4.47 kilo ohms. That's taking 4 squared plus 2 squared square root, and I get 4.47. So I'm assuming that we can all use our conversion between rectangular form in complex numbers and polar form. And then our angle is the inverse tangent of 2 over 4, and we get 26.6. So my impedance value, the total equivalent impedance for these two components that are connected in series, is 4.47 kiloohms with an angle of 26.6 degrees. So my goal is to figure out how much current is flowing through these two components. Together I could put these, and I haven't done this in the picture, but I could have taken this resistor and this inductor and just replaced this circuit with a box, and that box would be my impedance, and that impedance value is the value we found on the previous slide. My goal is to figure out the current. I know the voltage across that impedance value is 10 volts and it has an angle of 30. If I write that in phasor notation, that's 10 volts divided by the square root of 2 to put the effective value in there, which is 7.07, and then the angle is 30 degrees. Since I know the voltage and I know the impedance, similar to Ohm's law, I can figure out what the current is. The total current going through that circuit is just the total voltage over the impedance, V equals IZ, or I equals V over Z. Using my phasor notation, I can write this as the voltage 7.07 with an angle of 30 over the impedance 4.47 kiloohms, phase angle of 26. I can divide 7.07 over 4.47. I get 1.58 milliamps. And then I can take the angles and figure out the angle when I divide. This is 30 minus 26.6, so I get 3.4 degrees. So the total current that's flowing through the 4 kilo ohm resistor and the 2 Henry inductor is 1.58 milliamps, angle of 3.4 degrees. So it is shifted from the voltage a certain amount. Once I know the current that's going through both of those components, I can use the equivalent of Ohm's law for impedance, and the voltage across the resistor will be the current that's flowing through that resistor times the impedance of that resistor. So I take the current that I found, 1.58, angle of 33.4, multiplied by the impedance of the resistance, which is 4 kiloohms, angle of 0, and I get 6.32 with an angle of 3.4 when I add those two angles together. So the voltage across the resistor is in phase with the current that's going through the resistor, which is exactly what I would expect. The voltage across the inductor is just the current that's flowing through the inductor times the impedance of the inductor. So this would be the current that we have above multiplied by the impedance of the inductor, which was 2 kiloohms with an angle of 90. 2 times 1.58 is 3.16. I can figure out the angle when I multiply by adding the two angles together, so it's 93.4. And what I find is that the voltage across the inductor is leading the current through the inductor by 90 degrees, which is exactly also what I would expect. If we wanted to, we could check Kirchhoff's voltage law, and what we expect is that the total voltage should add up to the voltage across the resistor and the inductor combined together. When I add these two values together, I have to understand that I have to add them as phasors. So I can't just take the numbers that are in front, like the voltage across the resistor 6.32 and the voltage across the inductor 3.16. If I add those two numbers together, I don't get 7.07. And the reason for that is because these are not maximums at the same time. They are actually shifted from one another. So if I wanted to make a plot of this, I could draw in the voltage, which is at an angle of 30. I could draw in the current, which had an angle of 3.4. We found that value. I could draw in the voltage across the resistor, which was at an angle of 3.4. And I could draw in the voltage across the inductor, which was at an angle of 93.4. So a couple of things that we should notice is that the voltage across the inductor added to the voltage across the resistor should add up to the total voltage. And if you think about these as vectors, which we've done before with complex numbers, then the parallelogram method would work. And so if I took this vector and I connected it head to tail over here, I am getting that total. I also noticed that the voltage across the resistor and the inductor are shifted from one another by 90 degrees. And also an important fact is that the voltage across the resistor is in phase with the current through the resistor, as it should be. The voltage across the resistor and the current through the resistor will always be maximums together and minimums together. And here's my inductor voltage. It is shifted from the current by 90 degrees, which is also what I expect. The current through the inductor, the voltage across the inductor leads the current through the inductor by 90 degrees. Another part to this question asked us to look at the total voltage across the circuit versus the total current in the circuit and how they are shifted from one another. And we can find that if we look at the voltage, which is at 30, and the current that's at 3.4, the voltage leads the current by an angle of 26.6 degrees. The fact that we get 26.6 degrees for how the total equivalent voltage, or just not equivalent, but the total voltage across the circuit compares to the total current that goes through those components, the fact that the angle between them is 26 degrees is important because if we look back at our total equivalent impedance in that circuit, the angle for the total impedance was 26.6. So that angle for our total impedance is telling us how the voltage in that circuit is leading the total equivalent current that's in the circuit, especially in series. And if we're looking at this as just one total equivalent impedance, one total voltage supply, and then the current that's flowing through it.